Hello and welcome everybody to this Fabric Espresso. I'm joined again by Bogdan, which means we're going to go deep into query optimizations, query processing and all that stuff to basically show you how Fabric ticks and how it works so fast. So Bogdan, what are we going to talk about today?
Good morning. As you remember, last time we talked about query processing and how we convert Parquet into the internal formats that are supported by SQL and Power BI. Today, we'll talk about distributed query optimization in Synapse SQL, in the new Synapse SQL.
Okay, let's dive in.
So planning and executing the queries. Let's start with what happens when data is ingested inside the warehouse. Typically, you ingest data in a warehouse through a SQL statement, through some sort of copy from, insert into, or whatever. When data is ingested into SQL Server, the SQL engine has the ability to lay data neatly on the one lake storage, right? So we are going to create blocks of data that share similar properties. We have the freedom to distribute data, such as, let's say, put Seattle on the left and Paris on the right. So as we ingest the data into the system and we store it onto one lake, we keep rich statistics. We keep lists of files, the size of the files, and the distributions of data in those files. And this statistics allows us to group the files and the row groups inside the files into data cells. These are groups of rows that are in a permanent or temporary table. We'll just talk in a second about this. But they're groups of rows of more or less the same size. These are work units. As you imagine, when we do a parallel processing of massive amount of data, we need to split the data into smaller chunks. Now, you may recall here, if you are using the dedicated SQL in Synapse, that we have exactly 60 distributions of data. In Fabric, we are way more flexible. We find the optimal data size, and we can have an arbitrary number of distributions depending on the volume of your data. Now, as you may have heard, in Fabric, SQL works in the same way, uses the same code on top of data warehouse and on top of lakehouse. And in the lakehouse, obviously, we do not control the ingestion. So what do we do in the lakehouse? In the lakehouse, we have this process called metadata discovery, where we discover the Parquet files in one lake storage. We learn about their size, we learn about their distribution, and then we assign different fragments, either full files or fragments of files, to data cells. The purpose is the same. One way or another, we are going to end up with units of work that are more or less equal in size, and we have lots of statistics about these units of work. So this set of statistics, this deep knowledge of how data is laid out, is critical in order to give us good performance. And once we do this, either metadata discovery over lakehouses or ingestion and tracking of distribution in the warehouse, we have a unified view of all the data in the lake. We have statistics. We can estimate the cost of performing different operations on top of these data cells. We can do efficient cell skipping if we know, for instance, as I was telling you, that Seattle is on the left and Paris is on the right. This trick of discovering the distributions as they're laid out in data allows us to support any kind of partitioning and distributing algorithm. For instance, we can use the Z-ordering or the Hive-style partitions that are frequently used in the Spark world, or we can use the hash distributions that are frequently used in the data warehouse world. So let's see what happens when we actually execute the query. I'm looking at a very, very simple query, which is counting the rows from joining two tables that appear in the TPCH benchmark, orders and line item. All right? So I have a very simple join here. We're joining these two tables and computing the count. The query is typically hitting the front end, the SQL front end, and is triggering first the unified query optimizer. The query optimizer is going to produce an execution plan, and you don't need to squint yet because we are going to go in details here. The execution plan is very similar to what you have today in SQL, except that it has these new nodes, the data movement operators. These are the operators that are describing how data is moving between different compute nodes of the massive parallel processing system. So let's look a bit at this plan in details. The first two things that are happening in parallel are the tasks that are scanning the two tables that we are joining, the orders and the line item table. As we read data from the two nodes, you see how data is being shuffled from wherever we are reading it into the potentially a different node or the same node where we start matching the data. Again, hash match, inner join, these are operations that you have already in SQL, so you should be familiar with this. It's only shuffle that is a new thing. Now, Keep in mind that line item is a huge table. In TBCH 1 terabyte, it has practically the whole terabyte happening in line item. So that means that this task of scanning line item may be distributed across multiple compute nodes. And that means that each of these compute nodes is going to do its own join. And then we do partial matching and partial joining. And then once again, we are shuffling these partial aggregates to a control node where we are bringing all the results together. This is very, very much like a map reduce algorithm. You may remember we talked about this in 2005, 2006. Now, as I said, the partial aggregates are getting marshaled to the control node. Then we do one more final aggregation. It's the task that is happening here. And then we extract the scalar, the count that was requested on the query, and return that to the user. So again, the query plan is split in tasks. Each of these tasks represents more or less a common SQL operator. The tasks are connected to each other through the data movement operators, which are specific to the MPP query plans. And now each of these tasks, logical tasks, are actually executed as one or multiple physical tasks, because if you are doing these logical tasks over a large amount of data, we are going to create many replicas of these logical tasks. These are the physical tasks, and each of these replicas is going to get executed on one or multiple nodes. So without further ado, we discuss about query optimization. We discuss how the query plans in Synapse SQL are more or less similar to the query plans in the regular SQL, except that they have a depth associated with the conversion of logical tasks to physical tasks. And this depth is what takes us to the MPP architecture. And we have these connecting nodes, the data transfer operators, shuffle and compute to control node, which are bringing the data together into the final result that we are going to present to the user. This is more or less how query optimization works in the new SQL. This is how distributed query plans are being created and executed. And next time we will talk about the distribution of work across multiple nodes.
Okay, awesome. That basically shows us how we get those query plans and how it's delivered into those different tasks. Awesome explanation. Now, if you have any questions about this, make sure you write them in the comments. If you like the video, give us a thumbs up. And if you want to see more of this Fabric content or the previous videos, make sure you subscribe to this channel and you get more of this Fabric goodness. As always, from the Fabric Espresso team, this is Stijn and
Bogdan.
Thank you very much. Bye-bye.